Okay, so this is, I think, part 2 of this problem. It was just becoming a very long video. So it started out looking like this. We had a compound shaft, drive several pulleys. We have segments 1 and 2, which are hollow aluminum, 3 and 4, which are solid steel, I believe. Where are they? Solid steel. We were given G. We had to find the maximum shear stress. We had to find, and now we're going to be working on rotations. So the phi part. So here's the information that we have. I kind of sketched it back out. So here is this was our internal torque, our resisting torque, okay, with units of pound-feet. And then we calculated shear stress with units of PSI. And where I have positive torque, I have positive shear stress. Where I have negative torque, I have negative shear stress. And even though we have the same torque between these two gears, because I have two different materials, solid this way, hollow this way, aluminum and steel, they may have the same shear stress, but they will have a different, they may have the same internal torque, but they will have a different shear stress, because torque or shear stress is a function of torque and geometry. Okay, so their torque is the same, but their geometry was different. And again, we have negative torque, negative stress, positive torque, positive stress. Okay, so now what we need to do is find that angle of twist for each piece. So my generic equation is TL over JG. And I need to set this up much like we've been doing. And we are going to look at the angle of twist. And I'm going to kind of leave some space so we can graph out the angle of twist. But we want to look at the angle of twist of this section right here, which was E to D. And that's going to be TED, LED, JED, GED. My internal torque was 95 pound-feet, 12 inches per foot. Length, if I go back and look, it was 54 inches. Divided by J, pi over 2. We have that radius, which I've written down our properties and geometry, So I have 0.75 squared, and then G was 12,000 KSI. And I'm going to do a quick check. I have pounds and I have kips. So I need to divide up here by 1,000 to get those pounds into kips. And my batteries died in the calculator. So we're going to see how this works on my phone. And I may just have to resort. Okay, so I'm really sad without my calculator. 95 times 12 times 54 divided by 1,000. And I get 61.56 on the top. And then on the bottom, I'm going to have 3.1416 divided by 2 times 0.75, 0.5, 5 times 12,000 equals, I get 5,964 on the bottom, so we get 61.56 divided by 5,9, and I get an angle of twist of 0.010325 radians. And I think that my rounding is going to be off because of the way I did this. So you may end up with a different number if you're carrying your numbers through. And I can sit down and I can find from D to C. So I have torque of D to C, length of D to C, J of D to C, G of D to C, and my torque was, come back up here, negative 175 pound-feet times 12 inches per foot and its length was also 54 inches. And J is pi over 2. That outer radius is 1.5, and my G was 12,000. KSI, again, kips and pounds, so we need to divide by 1,000 up here to make proper units. And note that I'm negative internal, negative stress, negative torque. So I'm going to get a negative rotation of negative 0.019014 radians. Okay, now got to come over here and look at this segment. So I have phi from C to B equals torque from C to B, length from C to B, J from C to B, G from C to B, and my internal torque was negative 175 times 12 inches per foot times a length of 36 inches times 1 over 1,000, to put that in kips, divided by pi over 2. Remember, it was hollow. It had a 3-inch outer and a thickness, so I put this into a radius, which is C. So I have my outer radius of 1.5, and then my inner radius is 1.5 minus the thickness, which is 1.375. So I have 1.5 to the 4th minus 1.375 to the 4th. Okay, that's my J. And then when we look at G, we have 4,000 KSI. My units are all inches. I've got this into inches and into kips, inches and kips. And I'm going to note again, it's negative. So I'm going to have a negative angle of twist of negative 0.008086 radians. And then I'm going to do the same thing from B to A. Torque B to A, length B to A, J B to A, G B to A. And when I calculate all of that out, it's positive, and I get an angle of twist of 0.060067. So now, because I'm referencing everything back to A, everything said with respect to A, okay, with respect to A, I can draw a torque diagram. And my torque diagram is going to come from A back to the left. So if I start here, here's my phi, and by torque diagram I mean angle of twist, and my units are radians. So if everything is with respect to E, then I'm going to have 0 right here at A, okay, with respect. I have the angle of twist in that segment is a positive 0.60067. So we are at 0 at A. That's our reference point. It says everything with respect to A. So we're going to twist. And we have a positive twist of 0.060067. Okay? Then I have a negative twist that's in that next segment. A negative twist. So I'm going to put in 0.060067, okay, minus 0.008086 equals, did I subtract that? Okay, 0.51981. So I'm starting here at positive, I'm subtracting because it's going, the angle of twist is going in that other direction. There we go. Okay, positive. It's going in that other direction. So I'm going to take 0.060067 minus this, and I get 0.051. So we're just a little bit left. 0.051981. Then, as I continue to move, I'm going to have another angle of twist. It's also negative, so it's minus 0.019014 equals, and I get this angle of twist of 0.032967. So I've come down even farther. And now I can add the angle of twist from segment 1, so plus 0.010325 equals. And I get an angle of twist of 0.043292. So it comes back up. Okay? So if I want to know the angle of twist from A to C, okay, from A to C, remember here's A, B, C, D, E. The angle of twist from A to C, it's a positive angle of twist. So we're twisting towards ourselves coming from the right. If I want to know the overall angle of twist at the end of the beam, I have an overall angle of twist. It's positive, so it's coming towards me, 0.0432. So even though we had these negatives right here in the middle, because of our material properties and our geometry, we never switch back over to a negative angle of twist in a shaft. Everything stays positive. It's just a little bit different degree of positivity as we move back down. So again, I calculate it for each segment. Everything was with respect to A, so there's my starting point. And then I just either add or subtract depending on if it's positive or negative. And that came from whether my torque was positive or negative, and likewise my shear stress is positive or negative. And just sum it up, it's a lot like the delta. This could have been internal normal force, this could have been internal stress, P over A, and this could have been my delta. And at the wall, I wouldn't have any displacement, but as I went down the length of that shaft, I would have displacement. So it's the same thing, just a different application because it's a different stress.